Okay. Hi, everyone. I'm David Hendricks, and this is my colleague, Jonathan Zhang. We're firmware engineers from Facebook, and today we're going to talk about open system firmware from scratch. So we're going to go over a little bit of background, what Facebook is doing and why. We'll talk about the build system design and how we are enabling our partners to work in this ecosystem. So first off, why does Facebook care about firmware? Long story short, we're a big company with many computing devices being developed and many different use cases. And as all of you know, firmware is that thing that turns your useless pile of sand and circuits into something that's actually usable by your operating system. So it's pretty important, and we have a lot of different devices. We're working on enabling compute and storage devices with OSF, but we also have networking systems deployed. We have telecom devices deployed as part of Open Cellular, which is in TIP, and we're also working on some embedded devices too. So standardizing on open system firmware will help us accelerate the development and deployment and do better with support. So for the purposes of this talk, we're describing the coreboot and LinuxBoot work going on in OSF. You'll also hear a lot about OpenEDK2 today, which shares many of the same motivations. So a lot of this stuff, same across work streams. Why is open source? So open source and transparency are increasingly important. As you all know, firmware is complex, it's highly privileged, and cloud service providers are ultimately responsible for anything that happens on their machines. You don't want your CEO being called in front of Congress for any reason, so just. So traditional firmware development and support model has basically been, the silicon vendor provides modules to a partner who then packages it up into their framework and sells it as a product to like an OEM or an ODM, who then sells the product to the customer, who's not supposed to know or care about what goes on in firmware. The hyperscaler model is turning that on its head. Hyperscalers are vertically integrated. We're involved with everything from sourcing of components to the development phases of the projects throughout EVT, DVT, PVT, et cetera. And of course, we are our own customers. So we're responsible for putting these things in the data center and deploying them and supporting them throughout the lifetime of the product, and then eventually decommissioning them. So basically, the hyperscalers have broken the traditional firmware support model, and we're looking into open source as a solution. Another obvious motivation is debugging, which was mentioned earlier. If something goes wrong, we want to be proactive rather than just reactive when we need to report and solve an issue. We do find the OSF has a more modern architecture in that, in our opinions, less is more. So we want the silicon in it to be as minimal as possible and then jump to a full-featured kernel, Linux in our case, as early as possible. And the idea with that is to reuse runtime components to boot into the runtime environment. This is also very familiar to our engineers. We have many teams and organizations of engineers who specialize in supporting Linux systems. So by doing it this way, we're able to leverage their talent. And of course, there are other motivations too, like fast boot time. Who doesn't like that? So I'm going to take a moment to describe the architecture that we're pursuing with coreboot and LinuxBoot here. So on the far left, you see coreboot with UEFI in the form of FSP. So as was just described, FSP is the UEFI PEI modules and perhaps some other parts that are wrapped into a package, and there's an API around it that you can call into from various firmware frameworks. LinuxBoot is, as the name suggests, a Linux kernel with an embedded environment that contains tools for loading and executing the target OS. The idea, of course, is to do the minimal silicon initialization and jump into LinuxBoot as early as possible, and then use Linux to boot into the target environment, which in our case is Linux. So this gives us the same production quality runtime drivers, network stack, storage and file system support, encryption libraries, and apps in our boot time environment that we're already supporting in the runtime environment. We can easily incorporate open source user space tools and scripts, as well as develop them in-house. And we can package, build, test, debug, and deploy on our schedule. So this reduces the turnaround time for building new firmware images And this is becoming increasingly important now that more firmware is being signed. So you don't necessarily want to have to, request a change to be made and then have it re-signed and then, sent to you through email or something. That's a pretty miserable workflow. And of course, everything is transparent and reproducible, at least to the maximum extent possible. So we can account for the firmware components, we can measure them, and we can verify those measurements independently. So we like this architecture because we feel it suits our business needs. And of course, the other companies, hyperscalers, government organizations, universities, et cetera, have their own business needs and might want to plug in various devices and use them in different ways. We're not trying to dictate any of that, but this is what we find works pretty well for us. And in the big picture, we're orienting ourselves around a modern open source code development ecosystem for firmware. So again, this means accountability, knowing what goes into the firmware and where it came from, scalability in terms of our engineering resources, utilizing our own internal resources more effectively, and also inviting external collaborators to join the effort. I mean, we've already been collaborating with like Google and HPE and IT Renew and others in this effort. And we also, in addition to the actual task of booting a system, we realize that testing is becoming extremely important in order to get people to buy into this new ecosystem. And so we're working, especially Andre over there, we're working on a modern continuous integration and testing system that we're going to launch in the public soon. And with multiple parties involved, it's very important to provide immediate and actionable feedback when a patch comes in. So that keeps the top of the tree building for everyone and working for everyone, and also gives developers something so that when they send in a patch for their device and it breaks for someone else, they know that they need to go in there and fix that right away. So that's important. OK, so that's the background, and with that, I'm going to hand off to Jonathan, who will discuss the build system design.
Thanks, David, for explaining the problem we are trying to solve. So, that's a motivation. What architecture we choose and why. So now that's a very beautiful plan, right? But then you might ask, now what's the next step? So the next step is actually making a product out of it. So we are working on this engineering process. For us, we believe in open source development because we believe the strength of the community, right? A community is always bigger than a company. So we want to enable, we benefit from our community, and we want to enable our community. So this is what our plan to enable the community. So first, let me go through the build system design. I clicked on something that got lost. I should just do that.
Sorry, one moment. Technology. It's amazing this stuff works at all.
It really is.
I should just do that. Okay. Got it.
Sorry about that.
Got it. Okay. So for the this is the build steps. So first, we build the uroot. So uroot is our choice for the Linux user space. init-run-fs. So we use the init-run-fs source code. We make the init-run-fs. And then we give the image to the kernel build process. So just take any kernel. Like we use our Facebook kernel, but it's not too much different from upstream kernel. Upstream kernel should just work as is. So with that, we built a LinuxBoot payload. Together with LinuxBoot payload, we have the coreboot source code and the silicon vendor binary blobs. The silicon vendor binary blobs, in case of x86, that's what the previous presentation talked about, like FSP binary, FSP header, ME image. So all those kind of things are necessary to turn into a full firmware image that you can flash to the flash. Now I'm going to go through the component one by one. So the first component is the build environment. So for coreboot, to build the coreboot ELFs, it contains its own cross toolchain build. Those toolchains, it's used as is. It does not depend on your build machine's tool. It's self-contained. And then the toolchains for other components, with the latest coreboot, the GCC version needs to be no later than 5.0.0. And in our build script, we check that. In future, we also plan to use Docker so that the identical build environment is used wherever you build it. You need to run FS. So there are many ways to build you need to run FS. Facebook's choice is something called uroot. Uroot is something like a BusyBox. The language we use is Go. So Go is a modern system firmware, system software programming language. That we believe that makes the user space application development a lot more efficient and safe. It has built-in testing facilities. The Go language actually has a very strong community. uroot is a full Go userland with Linux bootloaders. The uroot community has built hundreds of Linux commands with Go language. When we build the beauty of uroot is that when you try to fit the you need to run FS into Flash where you have a size limitation, you can build it as a binary like a BusyBox. But when you are just doing the development and you do a lot of iterations, you can put it as source-based. Some of the binaries, because we have not translated it to Go, we could include the binaries, static linked binaries like flash run or DMID code into ED run FS. Like for the DMID code, we are in the process of translating it into Go language. Linux kernel is the same kernel used in the runtime environment, let's say for the target OS. So the motivation we use Linux kernel to do all those things is the drivers are production quality and familiar interfaces. So instead of, in UEFI, you have all the drivers for the devices, for file system, and for networking. But in this solution with LinuxBoot, we just use the Linux kernel drivers. We configure the kernel so that the configuration is minimized for size consideration. So that it can put Flash and we have more rooms for user space commands. We use kconfig. That's the same as what Linux kernel uses. Coreboot. To configure, so coreboot has a vibrant community. It supports hundreds of boards. And it's particularly dominant for the embedded environment like Chromebook. So it has a very, very rich set of features. You use kconfig to configure it. Coreboot, in the initial stage of coreboot, it calls the FSP to initialize the silicon and to set up memory, things like that. So we just use the FSP binary and the FSP headers provided by Intel. The same FSP binary is used by other bootloaders such as U-boot, like Slim bootloader. It's detailed in the previous presentation and in the next presentation, ready from Intel, and we'll go through that. So with coreboot, coreboot has a flexible framework that is easy to integrate features such like verified boot and other features. Another component, a group of components, is the silicon vendor's binary blobs. In terms of Intel, that would be IFD, ME, and microcode. Put them together. In the bottom, there's a build environment. And then next up is the LinuxBoot. It's a glue layer. The glue layer would include things like build scripts, build configurations for the kernel, configurations for the user space, configuration for coreboot, patches, right? So we cannot, in our production development phase, we cannot always, it's our goal to use the upstream as is. But there are always all kinds of reasons. Sometimes it's because of schedule reasons. So we would occasionally have some patches. And then initRangFS has a lot of components. Like it has the Go language build environment there. It has the uroot stuff, and it has the binaries. And then kernel source code, and then coreboot. You have the coreboot core code and the coreboot third-party modules, like vboot and the blobs. So that comes together. That's a lot of components you have to pull from various sources. So to solve that problem, we use a build configuration file, which would describe what components are included to make a build, where to get a component. You could get it from upstream. You could get it from a mirror of your company. You could get it from a tarball. Which snapshot will be used for a build, and what's the directory structure. So that we are all defined in the build configuration file. Configurations. So build configuration is part of the firmware configuration. So how do we solve the issue of firmware configuration? We use the Google Chrome OS VPD binary blob. In the binary blob, we store all the firmware configurations, including the build configuration. For example, we put the FSP configurations there. FSP has a concept called UPD. That's how you customize the FSP boot behavior. So that information is put there so that user can change it and then reboot, and then FSP will have a new behavior. Other configurations such as the boot log, verbose level. So now in terms of the build configuration, we have two variables there. One is called overall version. That's a schematic version of the entire firmware. Right? That's the thing that everybody refers to this firmware, to the firmware. Internal versions is a breakdown of all the components and where to get it, how to get it, what's the snapshot, all the information out there. So Facebook LinuxBoot repo, it includes the build scripts, build configurations, and kernel and coreboot configuration, and patches that will be upstreamed at an appropriate time. The build steps becomes as simple as you clone the LinuxBoot repo, you cd to the LinuxBoot repo, run a build command, and then everything will done for you, provided you have access to all the repos. So let's say in Facebook internally, we point our build configuration file, we point all the repos to our internal repos. And then in the public case, all the repos will be a public repo. So this build configuration concept gives people the ability to solve different scenarios. Like, give me an image. How is this firmware image built? You just run a VPT tool in your build machine or any machine, any Linux machine. You have the VPT tool. You run the VPT tool, you can get the internal version's VPT variable. You can immediately know what components are included, how they are built. Now, you have a target. The target had a crash. How do I debug? Right? You boot the target into the uroot shell or OS shell, given you are able to boot into uroot shell or OS shell. Then you just run the VPT command. We have VPT command both in the uroot shell. That's the UEFI shell equivalent. It's our firmware shell. Or you can go to Linux shell, run the VPT command. Now, what if I cannot boot into uroot shell or OS shell? What can I do? So in that case, you can also run the flash run image command. You take the flash out, right? Get the image out from the flash, and then you can dump the image out, and then you can run VPT tool on a debug machine. Now, given the build information, I obtain from the VPT variable, internal version VPT variable, how do I replicate the build? Because it includes all the information. Then you just need to clone the LinuxBoot repo and rebuild it. You get everything back. So next item is how do we plan to enable our partners and our community? So Facebook cannot do this alone. We have to work closely with our partners. Partners means silicon vendors and our ODMs to turn it into a product. And we want to work with the community. We want to enable the community. We want to get in community's feedback. So we design the system to enable that. This is the timeline or milestones for OCP platform submission. So in yesterday's keynote, Bill and Ram mentioned that in 2021, OSF becomes a checklist item for OCP platform submission. So if we look at the timeline of how an OCP platform gets created, then during the EVT, DVT, PVT phase, that's mostly the closed door partner collaboration. And as soon as everything is good, it's going to be mass production environment, and all the quality issues, legal issues are solved. Then the OCP platform will be submitted. So what it means by OCP platform gets submitted. So the checklist include hardware design specs, schematics, everything you need to rebuild a platform by any other company. And in the meantime, this new OSF request is that you also need to have an OSF software there to enable other people to be able to work on this platform, to be able to power it on. So at the MP phase, the machine in our data center runs OSF happily, and in the meantime, the community will be able to access everything needed to build and customize for your platform that is based on the OCP platform. Partner collaboration. when we work with our partners, we before the OCP submission, we adhere to strictly upstream model. So we want all the new code to go to upstream first. And then our build system actually grab it from a mirror of the upstream. So Facebook grab it from the upstream. So the developers, whether it's Facebook developer or our partner developer, they contribute the new code to the upstream. So upstream community can give feedback, know what's going on, and then once it's in the upstream repos would be all the repos we have to touch, like coreboot, uroot, everything. I also want to point out in terms of and then the Facebook internal repo will get the latest update from upstream, and we push it out to private repo that's shared with our partner. Post OCP submission, in that case, it's submitted to the OCP, and then Facebook becomes a community member. So Facebook is merely a community member, like any other community member. All the pieces are downloadable, redistributable, and we will work with the upstream community to enable continuous integration and test. Because we have a continuous integration and test system in-house, and we will do a very similar system for the upstream community, enable the upstream community to do it. And OCP members can customize it for their infrastructure as needed. OCP members can get community support or can get professional support to turn it into production for them. Our colleagues, Andrea is working on contest. So that continuous integration system will support continuous on-demand and per diff tests. It has plugins to accommodate different test infrastructures. In Facebook infrastructure, it's very different from upstream test infrastructure. So the system is designed to be flexible, to accommodate them. So you just need to develop plugins to cater for your particular test infrastructure. That will also be open sourced. Call to action. So join us in the OCP OSF project. And join the related OSF communities, LinuxBoot, uroot, coreboot, and play with the off-the-shelf OCP platform, such as the WinWin Tioga. So you can just buy a WinWin Tioga online, put on your desk, plug into wall, and then go to the LinuxBoot repo, download the README file, download the source code, you're off to go and explore it. Thanks.